we are now going to hear from Samena Mohammadi of RISE. This is the Research Institutes of Sweden. We had a little technical difficulty before, but I think we've got it all ironed out. And so I'm delighted to have her with us to talk about scalable functional encryption within the context of federated learning.
Hello, everyone. Sorry for the technical issue. My name is Samane. I'm industrial PhD student at RISE, Research Institute of Sweden. So today I'm going to talk about our recent work, which was a joint work with Vasilis, who is a PhD candidate at Eindhoven University. So this work was like a joint collaboration throughout this project. So our recent work called EncCluster, which means that scalable functional encryption in federated learning. I just skipped this introduction to federated learning, but from the privacy point of view, federated learning can preserve the data on a local devices and can minimize the data exposure to the outside of the system. If we compare it with machine learning, it's enhance and preserve the initial level of privacy, and also support to regulatory compliance such as GDPR and AI Act, and minimize the leaving and minimize the data exposure to the outside the system. But when it's come to sharing this model parameter with outside, there is a possibility of leaking sensitive information of the user, of the training data set of the user. A malicious client inside of the system and outside of the system, by having a different level of access to the model parameter or architecture of the neural network or different type of parameter during the training round, and can conduct different type of attacks such as model inversion attack, membership inference attack, and property inference attack. And by accessing this type of the model parameters such as weight and gradient, can reconstruct and access some sensitive information. So let's look at this example that I captured from the mentioned paper, which is about the deep leakage from the gradient. So this example shows that how gradient inversion attack can be pose a significant sharing this model parameter during the federated learning can pose a significant privacy leakage during a training round. So the aim of this attack is reconstruct or infer some sensitive data from share gradient or model parameter. And this image, the top on the left show the original image, and the another image show that the attacker tried to reconstruct this image from the share gradient of the client. So as we move to a row of the image by moving forward and in each iteration, the attacker can improve and make it like a clear image, and exactly at iteration 218, it's exactly look like the same image as it's used for the training. So this show that how the sharing and exchanging model parameter between the client and server can pose a significant privacy leakage during the training round. So to preserve the privacy in federated learning, we need to apply additional privacy preserving mechanism together to federated learning to prevent this kind of the leakage and any threat from the entities from the client, server, or outside of the system, and preserve the privacy. So some of the common one is using an encryption-based approach, especially in homomorphic encryption and functional encryption method. So let's look at these two methods in a more details. So homomorphic encryption is a form of encryption that enable performing computation on encrypted data without decrypting it, which means that the client encrypt their model parameter and share it to the server, and the server, without having access to this encrypted model parameter and decrypting, can do aggregation on the encrypted model parameter without accessing to this original or model parameter of the client. So it's provide the individual level of the privacy that the client model are hidden from the server, and provide also secure aggregation and also communication. So even the eavesdropper cannot access to this access to the encrypted model parameter without having the private key. But the main problem is here is it needs too high computational cost on the client side, which in federated learning scenario, it's mostly involving resource constraint devices, and it make it the training round slowing, like a slower training round, and overhead in the whole system. And another thing is the problem in homomorphic encryption is that system is vulnerable to malicious client, which means that all of the client have the same private key, and if the client share this private key with server or outside the system, it can easily decrypt this model parameter. So in the homomorphic encryption, the system is still vulnerable to malicious client if some of the clients acts as a dishonest or malicious behavior and share this key with the outside. It's still possibility to leakage of the privacy and security in the system. While functional encryption can improve and can defend this kind of the attack and a leakage in a system, by providing a specific computation on encrypted data and controlling what kind of the data can be decrypted. So this means that the only result of function can be a reveal rather than the whole individual model parameter. So let's look at when it's applied in federated learning. Consider that the client encrypt their model parameter and share it to the server. And so the server can just decrypt this aggregation by using the decryption, functional decryption key, can just access to the output of the result of the aggregation model parameter, and without and cannot access to the individual model update. And also the client have their own encryption and decryption key. So each of the client create their own partial decryption key. And in this case, if also someone share their own decryption key, it's not possible to access to other client and cannot access to decrypting this model parameter of each client. So in this case, the individual client updates are hidden even from the other client, and all of the client, they have their own private encryption and partial decryption key, and it's not shared between the client. And also this kind of system, decentralized functional encryption, provide the target privacy and control on the whole encryption and decryption process. But still, it's have some challenge when it's applied in federated learning. It's really complex to key management part, because it's needed to have a trusted third party to generate the whole key for the encryption and decryption and share it with client. And also it's applied the high computational cost on the client side. And still in a federated learning scenario, we have a resource constraint devices. And another problem is that we need to mostly this kind of the method mostly rely on fully trusted third party, which means that if these third party authority comprised, it's make it like a system, the whole system can be under risk for the privacy and security. So what we see here, when we apply a cryptography protocol in federated learning scenario, we can see like a secure federated learning dilemma, which if we want to have a higher privacy level in a system, it costs to like sacrifice the efficiency in terms of computation and communication, and in some cases effect on the model performance. So to avoid this kind of like a balancing, to have some balancing privacy and performance, we need to propose efficient and scalable cryptography solution when we want to apply in federated learning scenario. Because in this case, we need to make it more, because in federated learning scenario, we have this is a decentralized and clients have a decentralized nature, and we need to have a scalable, because the client can be a lot of client can be involved in a system, and also make it more efficient without adding more cost in terms of communication and computation to the system. So also by looking at the literature review and related work, we can see that most of the related work that use the encryption, homomorphic encryption, and functional encryption method mostly rely on fully trusted third party that generate their key for encryption and decryption. And also, they don't consider the efficiency when it's applied on federated learning scenario. So it's make it very high cost in terms of a communication and computation. To solve this problem, our work mainly focus on eliminating the need to fully trust a third party in a system, and make this encryption method more efficient and scalable. When we apply it to federated learning, it can be a practical for resource constrained edge devices. So we propose a method EncCluster, which means that a scalable functional encryption in federated learning, and our framework consists of 3 building blocks: model comparison method throughout weight clustering, functional encryption method, and also binary fuse filter. So I will look at let's look at it more closer to the client side. So in the client side, we do this local training as usual, and then apply the weight comparison method throughout weight clustering. So this weight clustering is cluster the similar weight into the similar weight by using the k-means. And then after we apply this weight clustering, we will have a 2 array. The one array can have a centroid of each cluster, and then the another array show the cluster weight mapping, which associate to the each of the weight assigned to the which of the cluster index. So then on the client side, after having this weight clustering, we apply the functional encryption on the just centroid of the each weight, and this is really smaller than the whole weight of the each client. And we just need to have the third party authority, and we don't need to fully trust it on this party, because we just apply this functional encryption on a centroid. And this party, without accessing to this weighting matrix, it's not possible to recreate or generate the weight of each client. So then for the a weight mapping matrix, we apply the binary fuse filter that hash this. Binary fuse filter is a probabilistic space efficient probabilistic data structure that generates map the data to some fixed speed, and also compute and also compact the data by using a hash function, and then create a fingerprint array. So for doing this and creating a fingerprint array for each position matrix, we need to seed value for each client. So this seed value is just shared between the client and server, and the third party authority cannot access to the seed value. So this is the main and key point of our method, that why we can remove the fully trusted third party in our method. And then on a server side, server get this encrypted centroid and fingerprint array from all clients, and then recreate the position matrix of each centroid, because the server has the seed value for each client, by using this, inserting this fingerprint array to the like a hash function that we use, and by using this secret and unique seed value for each client, it generates and recreate the position matrix of each centroid, and then form the client encrypted weight by replacing the index of the index with the encrypted centroid value, and then server combine all the partial decryption key to derive the functional decryption key for aggregation, and just access to the aggregated weight without accessing to individual model parameter of the client. So this is the whole of our framework. So the key efficiency point of our method is that we apply this functional encryption key, functional encryption method just on the centroid of the each cluster without applying it on the whole weight of the client, and also apply this efficient encoding of the position matrix of each centroid by using a binary fuse filter. And in terms of the privacy, and as we say that we remove this fully trusted third party in our method, which means that the server can reconstruct the position matrix, but still cannot determine the client weight based on this centroid. So this, if the server acts as a malicious party, just it can access to the like a weighting the position matrix of the each centroid, and the third party authority can access to this centroid of the each weight matrix, but cannot access to the position matrix of each weight. So it still cannot reconstruct the client weight of the like each individual client weight. So for the privacy analysis, we consider different type of threat model in our system, and to show how our method can defend against this kind of the like privacy leakage. So the threat model that we consider is honest but curious server, which means that the server can follow the like a whole protocol, but still have some like a curiosity about the model parameter of the client. And honest but curious also third-party authority that still follow the whole like a protocol, but still have some curiosity about the client model parameter. And dishonest client, which means that the client can collude with the server to get model parameter of the like another client. And we provide some analysis like mathematically or like a proof based on that. We assume that if we have an isolation or reply attack from the server side, how our system can defend against this type of attack, or if the server or client try to reconstruct some model parameter in the system, and also if we have like a comprised trusted third party. So we provide this kind of analysis in a paper. I'm not go to any details. If you're interested, you can check the paper analysis regarding the privacy and security analysis. So for the efficiency evaluation part, we consider the CFAR10 and 100 as a data set, and also we have 4 models to evaluate our method. And metrics, we use the accuracy loss compared to Fed average, data transmitted, the volume of data transmitted compared to the Fed average, and also encryption time measured by a second. And the baseline, we consider the Fed average with applying the weight clustering, CFL method that use the homomorphic encryption with gradient pruning technique, which is one of our previous method, and DTrustFL that combine the functional encryption with global differential privacy. So we compare our method with 4 baseline. Let's look at more on the like a performance. So for performance analysis, We consider different type of federated setting, IID-ness of the data, and considering different like a portion of participation from the client side and on like a different type of data set that we have. So if we want to just have some example, for example, if we want to compare it our method with dtrustfl that use a functional encryption, we make the data transmitted between the client and server 30 times less than this method, and encryption time 160 faster than the dtrustfl method. And just comparing our method with the homomorphic encryption CFL method, we make it 9 times less for the data transmission and 4 times faster for the encryption part. And also, as this method use the gradient pruning technique, so it's effective the accuracy. So we just compare our accuracy loss with this method. So as you can see from this, this part, we preserve the accuracy loss near to 1 to 2, but this CFL method is like a privacy loss is near to 2 until like a 4%. So we also have computational, in terms of computational efficiency, we show that by having a different key size in a encryption-based method, dtrust, CFL, and OR method, by using a binary fuse filter and without using a binary fuse filter. And this show that increasing the key size and execution time that takes for the encryption. As we expected, by having a larger key size, we require more computational resource and execution time. But take a look at the example on a Bitcoin key size, which is near to 256. Generally, they use this key size. So for our method, by having a binary fuse filter and not having a binary fuse filter in a blue chart, for the execution time, it takes just 2 seconds. But if it's come to dtrustfl, it's take 329, and for a CFL method, it's 7 seconds. And for the computation efficiency, we still have the different key size and data transmitted by comparing to Fed average. So our methods show that we have a more consistently data transmission amount by increasing the key size, which indicate that we have like a really efficient and scalable method when it's applied and having a larger key size. So by having the same example for Bitcoin, Bitcoin key size, we for the data transmission, if we have by having a binary fuse filter, we have a 1.2, and without having it, it's sorry, by having a binary fuse filter, it's 9.2, and by without having it, it's 1.2 times by Fed average. While this amount is for dtrust is near to 120 times of Fed average, and also for CFL it's 80 times to Fed average. So it takes like the data transmission volume by comparing when we just share this model parameter using a Fed average. So we also have some evaluation regarding the scalability of the our method. By using a different type of cluster size and also different type of key size, and showing this having a different number of cluster, how it's effective accuracy loss, and also different type of key size and data volume that share like during the training round. So, for example, in a figure B, we show that by increasing the cluster number, we reduce the accuracy loss, which is as we expected, because when we increase the number of cluster, it so the weight is not too much like the weight can be like maintain as a similar to the like a previous one without having or rounding it. And for the And the figure A show that the impact of cluster size and also different number of key size. And our method show that by increasing the security level and the key size, we have a slightly effect on the data volume that's shared between the client and server, uh, which is really slightly from the 0.2 till 0.3 across the all key size, which show that this method really scalable on the different level of the key size when we increase the security level. And we have also analysis on different type of model, neural architecture. And we want to show it the generalization and scalability of our method across the different model architecture by showing it the accuracy loss and encryption time. So we show the slightly our method show minimal accuracy loss across all the architecture, neural architecture and data sets, and even by having a larger model like MobileNet, we have a less impact on the accuracy loss compared to a smaller model. So as a conclusion and key takeaway, we propose and combine three building blocks: model comparison, decentralized functional encryption, and binary speed filter to encoding and we ensure the privacy preserving without compromising the efficiency in federated learning. And we in terms of communication and computation gain, we have a reduction near to 30 times, and in terms of communication costs, and 160 times speed of the computation by comparing to a relevant work and baseline. So we design a private and efficient federated learning paradigm, and which can be applied on a resource constrained edge devices. As a future direction, we want to advance the functional encryption method, which can eliminate the third-party authority from the whole system. And additionally, we want to take a look at adaptive weight clustering that dynamically adjusts the cluster size based on the model and task a requirement to make it more dynamic and based on the each architecture. Thank you for your listening. So here is our email. If you want to if you have any question, please reach out. And this is a barcode for GitHub and archive of our paper. So
thank you so much. Really interesting work. We're a little bit short on time, so I'll just ask one quick question, and that was, how would you, if you're a user out there, you're trying to build a federated system, these issues are a concern to you, and so you're looking at various options. What would be the scenario in which you would go for this solution? You know, sometimes people might pick homomorphic encryption. Sometimes they might pick differential privacy, perhaps. Depends on what the attack concern they have is. And so many of these are fairly well known. I guess the three most popular would be FHE or HE, homomorphic encryption, differential privacy, secure aggregation. They're the most three popular ones. I assume people who want to be resistant against these sort of privacy attacks that are building on top of federated, but basic federated. And so could you just, briefly, 2 or 3 lines, explain what is the kind of necessary conditions that somebody would say, okay, I've got these conditions, so I'm going to jump and use the method that you've presented very eloquently here.
Yeah. Thank you for a nice question. So I also I had a paper on differential privacy and homomorphic encryption, and what I see in different a method that I apply on different application. So differential privacy effect on the model performance, and it's sacrifice the accuracy of the model. But this method doesn't apply too much like a burden in terms of communication and computation costs. It's really simple and it's really easy to apply on federated learning scenario. I think in a case that the accuracy is if any case and this differential privacy also cannot provide a strong level of the privacy because it's add the noises to the model parameter and it's still vulnerable to different type of attacks such gradient inversion attack that we saw in like I mentioned in a previous slide. So if we need to have some slightly like a privacy method, we can apply this differential privacy, but we need to have some balance between the privacy and accuracy level. So if our application need to have some accurate result, we need to have like a adaptive noises to the model parameter and make sure that what is the best level of the noises to model parameter in terms of their like a system requirement. But when it's come to like a more sensitive data set, like healthcare system or financial like a data set, which is really sensitive and related to like a user data set or relieve some identity of the user, I think it's needed to provide really like a strong privacy to avoid and mitigate any privacy leakage in federated learning. So recently I joined to the project that they are mainly working on the healthcare system and psychiatric problem that's mainly like using the like a patient data set to provide like a diagnosing using this type of the data of medical data set, and they are suggesting to use the encryption method because they really care about this privacy and security of their data set, and they can provide a system that can provide higher computational resource for the devices, and they want to just want to have a strong level of the privacy, and they can provide the communication or computational cost, and in this case we can easily deploy this encryption based method in the system. So if I just want to say it, it's totally depend on the application requirement, and before going further for the privacy or security method, we need to know what is the exactly requirement of our application. Do we need to care about the accuracy or performance? Can we provide a strong can we have a resource enough resource to deploy encryption based method in the federated learning?
I see. Makes sense. Makes sense. Awesome. Yeah. Well, this is a critical issue for the community. Many people are thinking about this on a daily basis, given the type of data they're working with. And so, yeah, thank you so much for sharing your innovations. Very interesting stuff.